talked a little bit about continuity in live class this week, but I wanted to talk about the mathematical definition of continuity, and of course, why do we care? Why is it important? So, as I said in class, continuity is an idea with if a function is continuous, that means it is connected together, that you can trace along the curve without lifting up your pen or pencil. So, like in the examples from the book, lowercase function f and g, both of those would be deemed continuous because I can trace along it without lifting my pen or pencil. So those two continuous. However, looking at the rational function 1 divided by x minus 3, there's a problem with the domain. Dividing by 0 is not allowed. So at specifically x equal 3, we have a discontinuity due to the domain error that would be caused by division by 0. And as we can see, as we get closer and closer to 3 from the right-hand side, the graph goes down to minus infinity. And if we were to get closer and closer to the graph from the right-hand side, it goes up to positive infinity. That limit at 3 would not exist. And in the same sort of way, the function is discontinuous. And the reason I bring up the limit here is limits can help indicate problems with continuity. Domain can as well. But, we'll look at the definition here in a second. And we often refer to that as a break or a jump discontinuity. Because if I'm tracing it from left to right, like if I imagine that this is representing my bank account over time, well, on the left-hand side, it's dropping off a cliff and, falling very rapidly. And then over here, it jumps up really high and kind of comes back down. Obviously, we would not use such a function to represent most, like a bank account, but that's a metaphor I like to use just to visualize or imagine, behavior of a graph. Anyways, another case would be the piecewise function gx shown here. We'll look at another example of a piecewise function in just a minute, but we can see that there's a hole in the graph. Like if I was to trace along it from left to right, again, I can see that I get to this point, it jumps up here and then continues. We'd often call it a point discontinuity or a hole in the graph. And looking at the last one, another piecewise function where it switches from one line down to another, which is often called a break. But let's go ahead and look at the definition and look at a few sample functions to see if we can determine if they're continuous or not. So by definition, it says a function f is continuous at x equal a. Notice that the definition is specific to a location. If, first of all, f of a must exist, meaning that in order for a function to be continuous, it has to have a value at that point. Step B, or part B of this condition, says that the limit as x approaches a must also exist. So basically, it has to be defined, it has to have a limit, and part C kind of ties the first two together. It says the limit as x approaches a of f of x must be equal to f of a. So let's look at, say, for example, f and try to apply this to it. Let's just pick a random point on the graph. Let's just say this right here is point A. And that would be, correspond to that point. So we can tell that this point on the function is defined because it's part of the graph, right? There's no holes, there's no missing parts. Well, visually it's continuous, but that's not a proof, based on the definition. So it's defined because it has a value. The limit exists because I can tell that because the right-hand side and the left-hand side both head to the same point, and therefore the limit exists at that point. And part C, it says that the limit as x approaches a must be equal to the function value. And as we can see, both those limits are going to the same point, and it's defined. So all of those three things put together define continuity. And a continuous curve will always work that way. Because it's continuous, the limits always exist at those points. And they're just equals the function value. So looking at, we can see why these functions above are not continuous. This function is not continuous. Well, technically this function is continuous most of the time. We just say that it is discontinuous at a particular point. So we could say the example of capital F of x here, it's actually continuous from minus infinity all the way up until 3, where it has a discontinuity and then it retains its continuity on its domain, 3 to infinity. And basically, if we take the union of those two sets, we refer to this as the domain of capital F function. But technically, it also is continuous on those values. And actually, if you return back to our direct substitution property, which was in the slides from last time. But remember that I said that a polynomial and rational functions, they're always continuous on their domain. And we can see here, well, this is continuous on the values it actually works for. When it's not defined, it's not continuous at that point. Now, looking at these piecewise functions, they can have discontinuities all sorts of different places because we're essentially taking different curves and pasting them into a singular function. But like with capital G, we can see, well, the limit towards x is equal to 2, it is defined, but the issue is that limit is equal to 3. The function value is equal to 5. Those are not equal. So that one we'd say would fail the third condition, condition C of the definition. So this function is continuous everywhere except for at x equal 2. And you could say it has this continuity at that location. And same with function capital H. Here, it is defined at 1. The right-hand limit actually does approach 1, but the left-hand limit does not. So there, as again, we'd say that that limit does not exist because those two limits are not approaching the same point. So the limit does not exist. So that would fail condition B. So if it fails any one of those three conditions, it's not continuous, and that's that. So if you're looking at a function, that is where you want to look for. You want to look for obviously weird behavior where it breaks or has holes or something like that, or any errors within the domain. Because if it has a missing part of the domain, it immediately cannot be continuous because it has to be defined. And additionally, the limits always have to be in agreement. So let's look at a couple functions. It says, are the following continuous? F of 1 of x is equal to 3x minus 4. Well, straight off the bat, this is what we call a linear function, mx plus b, where, the slope is equal to the first, the multiplier on the x term, and the constant term is the y-intercept of this. So, we could imagine, really starting with a graph is the first way you could tell if something is continuous or not. And that's the easiest way. But it will have a slope of 3 and an intercept of minus 4. It'll look something like that. And a straight line, linear functions are always continuous because, well, first of all, polynomials are always continuous. That's just a general trait of that category of function. And another reason why, in my mind, why is continuity the most useful thing to know is because it makes limits a lot easier. Continuity, if a function is continuous on an interval, that implies that its limit must be equal to the value of the function. So if you know something is continuous, that means you can use direct substitution to solve the limit because it must be equal. And also, the other point of this is if you look at the graph of a function and you can see that it's continuous, that means you can use direct substitution to find the limits. And that prevents us from having to do algebraic limits like we were working on, which, as you can agree, are pretty tedious. Or it prevents us from having to do limits graphically or numerically. All of those methods take quite a bit more time. So summarizing, continuity makes limits a whole heck of a lot easier when it's continuous. And when it's not, then we can use those other techniques to try to figure out what is going on. So looking at a graph of 1 over x, the reciprocal function, that's the one that we looked at in last week's video. But on the right-hand side, it looks like sort of has that sort of half of a cup sort of a shape, and then on the left hand side it's the same sort of reverse pattern of a reciprocal. But this one, as we discussed, had a vertical asymptote at x equal to 0, or it had a discontinuity. So right off the bat, I know this is not continuous. So I didn't actually answer my question, but basically question 1 was continuous everywhere. So I'll just write yes, C2 yes, everywhere. And the question, when I ask you if it's continuous, that usually implies everywhere. So this function is not continuous at 0. I say it's not continuous everywhere. But you could say that it is continuous on the intervals of its domain. And what's more specific is to say, well, it's not continuous at x is equal to 0. And one of the reasons is, well, you can't divide by 0. It's not part of the domain. It implies discontinuity. But actually, that's the only discontinuity. Any other value will work just fine. You can plug in 1, 2, -3, 52, 1/4. Any other type of number will work just fine in function 2 here. Now, the third function, piecewise functions like the ones in these two graphs here, those always have room for discontinuity, especially at the interval where it changes from the first piece down to the second piece in the formula. Now, if we look at the two formulas for f3 of x, we can see that those are two different, they both are linear, right? Because we got mx plus b, mx plus b. So this one would have a slope of 0.5 and then plus 3 for the y-intercept, and this one would have a slope of 1 and have an intercept of -1. We looked at a piecewise function last week's videos, but I forgot to show you how you can actually graph these with your calculator. So let's go ahead and do that, just because that makes it a lot easier to determine if it's continuous or not. But I can also give you another trick for determining continuity of piecewise functions, which is even easier, but I think it'll make more sense when we're looking at the graph, why it works the way it does. So to graph a piecewise or any function, you can always go into the y equals menu to type in your equation. But with a piecewise function, we need to make sure that we want it to specify the intervals for the domain, because basically this part is only valid for the domain when x is less than -2, whereas the second part is only valid when x is greater than -2. So the way you can type in a piecewise function is actually if you just type in the first part in parentheses, close off those parentheses, and then you add a second parenthesis. This is not, I wanted to mention, this is not proper algebraic notation. This is just a trick to get these sorts of calculators to graph it. But basically, you want to then type in the x is less than -2. And the less than symbol is in your calculator. I believe it's in the test menu. Yeah, so if you go second math, you can access this test menu, and you can type in x is less than -2 in parentheses. And actually what this is really doing is it's telling your calculator, this is a logical operation that if the value of x is less than -2, it does nothing, or it multiplies it by 1. But if this value comes back false, it will multiply it by 0. So in essence, it's not going to change our graph in the interval, and it will make it disappear when it's outside the interval. So it works for the practices of graphing a piecewise function. And that's all you need to know, really. And then for the second piece, we want it to graph x minus 1 when x is greater than or equal to -2. So again, same deal. Type the first part in parentheses, second part in parentheses. Test math is greater than or equal to -2. And hopefully this will work. And then we can just say graph, and it should graph those two individually. So what I can see is I have a line on the left. That line has a slope of 1/2. And it would have an intercept of 3 if it made it there, but since it stops at -2, it will not make it there. Then the second piece of this graph, I can actually make this a bit bigger so we can see it a little bit better. The second piece starts at -2 and then continues. It has a slope of 1 and a y-intercept of -1. So this matches up with those two lines based on initial inspection. And I'll go ahead and create a sketch here in the notes. So we have something that looks kind of like that, and then it sharpens like this on the right-hand side. Also, the endpoints, since the left hand, or the first piece of the function when x is less than -2 ends when it gets to -2, we should put an open circle on that endpoint, and then there really would be a closed circle on this endpoint because that one includes -2 in its domain. Anyways, we can see that this is not continuous at -2 because it breaks, obviously, and so we can really easily see that it's not continuous at x is equal to -2. Now, it perfectly well could have, if we changed the intercept on one of those lines, it could have lined up, even though the slopes are different. So it could have looked like a line that has a slope for one part and then change slope. And this also helps us see, well, why are piecewise functions useful? In the real world, a lot of times things don't exhibit a common trend throughout their entire history. Sometimes they change slope, and a piecewise function is an easy mathematical way of showing this. But usually most real world trends are continuous. Things don't jump. But actually, if you think about the value of a bank account, it is something that is discontinuous, because as you deposit money, all of a sudden your balance goes up. It might be growing exponentially based on your interest rate, but it will have changes, very immediate changes that are not continuous. And also, so I wanted to go, this video is getting a little too long, but I wanted to wrap up. How do we figure out if this is continuous or not without having to look at the graph? So I don't even want to call it a trick, but the way you can strategize this is it's only going to be continuous if it's equal in both sides. Like if the left-hand limit equals the right-hand limit, and if the value of the function is defined. So what I would do is, since these are both continuous individually, I could just check, well, what happens at the endpoint? What would the value be? And basically, what is the left-hand side and what is the right-hand side? Really, if you set this one equal to this one, if it's continuous, they'll be equal at that point, and you can just plug in -2 to check. And if it's not equal, then there will be an imbalance. So let me go ahead and set it up, and then I think it'll become more clear what I mean. So if I just type or write out 0.5x plus 3, that should be equal to x equal -1. And this is, again, if it's continuous at x is equal to -2. So I can equate them. And I'm assuming I don't know if it's continuous, even though I already do know because I looked at the graph. But this, again, the point of this is, how do we figure out without a graph? And then I could just plug in -2 into both formulas to see what happens. So in the left one, I have 0.5 times -2 plus 3. And we can then check, is that going to be equal to -2 minus 1? Well, -2 times 1/2 is -1. -1 plus 3 is 2. And the right-hand side, -2 minus 1 is -3. So what I can see is clearly those are not equal. That's false. So what that means is that it is not continuous at x equal to -2. So if those lined up, they would be equal, and their limits would also be equal. So you could also look at the limits in the same way to do this, but I think it's just simpler to basically equate the two positions in your piecewise function and plug in the point where you have the potential for it switching.